Alright, so let us get along with today's proceedings. Now we have been talking about function spaces and all, and in doing so I hope that you have not forgotten what representations actually are. Today what we want to do is we want to remind ourselves what representations are and then go back to this abstract treatment that we have started. Now this is a slide that we have been referring to again and again, right. We had constructed the transformation matrices of C2V using oxygen and the 2 hydrogen atoms as the basis, and we got 3 by 3 matrices, one for each operation, and then we saw that we could block factorize these matrices and we got a 1 by 1 block which is 1 1 1 1, and that is associated with oxygen atom, and we got a 2 by 2 block, we got 2 by 2 blocks for the 2 hydrogen atoms, right. This was, I think, our first exposure towards representation. So what is a representation then? This 1 1 1 1 is a representation, 1 0 0 1, 0 1 1 0, 1 0 0 1, 0 1 1 0. This is another representation. What is a representation? Can we say it very simply like this, that it is a collection of matrices? We are talking about matrix representation, right? Can I say that it is a collection of all the transformation matrices corresponding to a particular base? Does that make sense? See, 1 0 0 1 0 1 1 0, 1 0 0 1 0 1 1 0. These are 4 matrices. What is the base for these matrices? The 2 hydrogen atom, and these 4 matrices make up a 2-dimensional representation, right. So representation is essentially a collection of matrices. What kind of matrices? Transformation matrices, and when I say collection I mean a complete collection, a collection of all the transformation matrices for a particular basis is called a representation. Does that make sense? Right? That is a representation, fine. And we had asked these questions, that how many reducible representations are there, how do I know whether a representation is reducible or not, how many irreducible representations are there. Number of reducible representations of course is infinite. So these are the questions that we started with, and then what we did was we realized that there is no easy way of getting the answers for these. So we have started developing this kind of abstract general treatment using the concept of function space, kind of functions that satisfy all these criteria, right. And we are specially interested in orthonormal basis functions. We are interested also in this functions that span a particular space. These have to be linearly independent. Is it necessary that all linearly independent functions are also orthonormal? No. No. If they are orthonormal, then there are some added advantages, but there is no hard and fast rule that if a set of functions is linearly independent, then they have to be orthonormal. If they are orthonormal, are they always linearly independent? Yes, right, but the converse is not true. Very good. And then we had introduced these transformation operators, right. So this is something that we need to remember very well. What we said is that by using the transform operator, we have essentially written that the transformed function in the transformed coordinate has the same value as the original function in the original coordinate. This is something that we have discussed at length, and then we also realized that I can write this OR Fk, where Fk is the kth function of the F set. OR Fk, the transform function Fk, is equal to sum over j from 1 to n djk of R Fj, right. So we are all okay with this. So when I am summing over j, am I summing over the column or the rows? Am I going down a column or across a row? I am going down a column, right. So how is this justified? Because how did I get D? Please do not forget these. How did I get dr? I got the dr matrices by transformation of the coordinates. Now I am talking about transformation of the functions. So what is clockwise for one is anti-clockwise for the other. That is why the rows and the columns get interchanged when I talk about the functions. Okay. Please do not get confused and think that we are making a wrong multiplication. Actually, I was confused about something like that last week, but then it fell in place. Fine. And these are things that we have learned already, properties, some properties of transformation operators. First of all, these transformation operators leave the scalar product of the two functions unchanged, and we saw how. The scalar product of two functions remains unchanged upon transformation. This is something that we are going to use today. It is important to understand that transformation operators are linear. What is the meaning of transformation operators are linear? It means if G equal to AF, where G and F are functions and A is a constant, then OR of G, that is OR operating on AF, is equal to A multiplied by OR of F, right? OR G is equal to A OR F, right? We are going to use this today. And I think this is where we had stopped last day. We said that transformation operators produce a unitary representation if orthonormal basis functions are used. Right now it might seem that we are taking a random walk in some strange function space. Actually we are not. All these are going to be required when we finally put our story together. So this is a very important property of transformation operators. Transformation operators produce a unitary representation if orthonormal basis functions are used. What is the meaning of a unitary representation? A dagger A is equal to E, right? Unit matrix. That is the property of what? Unitary matrices. I am asking what is a unitary representation? Yes, a representation in which all matrices are unitary. That is all. Please do not get scared by terminology. Okay? Unitary representation is one in which all the matrices are unitary, and you already know what is the definition of unitary matrices. A dagger is equal to what? A or A inverse? A inverse. If it is A dagger equal to A, then what is it? Hermitian. And when is it orthogonal? When A transpose is equal to A or A inverse? A inverse. Okay? Please do not forget these definitions. Now the point is this. We are saying that transformation operators produce unit representation if orthonormal basis functions are used, right? But who has said that all the bases that we work with are orthonormal? It's not necessary. We can work with other bases, right? The question is it possible to switch from some given basis to an orthonormal basis? Why do you want to make that switch? Because if you can do that, then your representation will become a unitary representation. Why are you at all interested in unitary representation? Because life becomes simple when the inverse of a matrix is simply its adjoint. Life becomes simpler when the inverse of a matrix is simply its transpose, right? But maybe that is asking for too much, right? We cannot expect that all our matrix elements will be real all the time. So it is better to talk about unitary representations. If they become orthogonal representations, well and good, we have to work a little less. Fine. Now, so how do I switch to an orthonormal basis? As we will see, we do this switch by using similarity transformation. There are other methods. If you read a book on matrix algebra, or if you read these appendices of Bishop's book, then you see there is something called Schmidt orthogonalization method. But that is too much math and no chemistry. So we are not going to talk about it. Similarity transformation is something that is very useful to us, and now we start seeing why. What a similarity transformation can do is that it can perform a switch of basis. You can start with one basis and you can go to another. In the next few minutes we are going to learn how. But please remember this, what a similarity transformation essentially does is that it switches from one basis to another. one set of functions to another. So, let us see how. Now, if you have to switch, then you need two sets of functions, right. So, let us say we have two sets of functions f1, f2, f3, so on and so forth up to fn, and g1, g2, g3 etc. up to gn, right. These are two sets of linearly independent basis functions for the same space. Make sense? Can we think of such sets? Can you think of two such sets? Okay, start like this, x, y, z, linearly independent. Now, I can say that, of course, I mean assume that my right and left hands are the same, they are not, right. So, let us say I have another coordinate system like this, right. Those three vectors are also linearly independent and they span the same space, right. This set as well as this set, both are going to span the same Cartesian real space, right. So, I can say these are f1, f2, f3, these are g1, g2, g3, right. Because nobody has said that, we are saying that this is x, this is y, but who has said that we should not turn it around? It all depends on which reference you use. Okay. So, these two kinds of x, y, z and x dash, y dash, z dash kind of basis functions can be used, right. But let me use something that is a little more tangible to us chemists. Let me use p orbitals. Can you think of two different sets of linearly independent basis functions for p orbitals? I think we have discussed this very briefly earlier. What are the three p orbitals that you know of? Px, py, pz, right. So, that is one set, say f1, f2, f3, px, py, pz. Is there any other way in which I can write the p orbitals? P plus 1, p minus 1, p0, that is right. Right? Will you agree that they span the same space? After all, we are talking about p orbitals, right. No matter whether we denote them as plus 1, minus 1, 0 or x, y, z, they span the same space. Okay. Are they linearly independent? Yes. If you add px and py, can you ever get pz? You cannot. So, they are linearly independent. So, they satisfy these conditions to be f and g sets. How will you draw the coordinate axes? These are imaginary. P0 is the only real orbital. In the second set, P0 is real orbital and it is along z, no issue. But P plus and P minus, you cannot even draw them in real space. No? So, the space that we are talking about here is not Cartesian space. It is a space of p orbitals. It is not real space. Understand? So, space is not something that should be taken on face value. By space, we just mean this collection. Remember what is function space? It is a collection of vectors, collection of functions. Okay, that is what I mean. Fine. So, now can you express say Px as, okay, let me do the difficult one first. Can you express Pz as a linear sum of P plus, P minus and P0? Yes, 0 Px plus 0 Py plus Pz, 0 0 1. What about Px and Py? I want to write an equation like this, okay, and if I believe what Atkins has to say, it is worked out in this page 337 of Atkins book, this edition, that this is the matrix Px equal to 1 by root 2 P plus 1 minus 1 by root 2 P minus 1, Py equal to I by root 2, then yes, that is it, right. So, this is worked out in Atkins, please go through it. The matrix that Bishop has written is different, I do not know why, but I believe Atkins because it is worked out very nicely. You can go through the working out. So, this is the matrix that we have. Let me call it curly A. I'll have a non-Carly A also afterwards. That's why I'm forced to call it Carly A. And this is where I got confused while reading Bishop's book, because Bishop conveniently jumped a step. So I disturbed a lot of people asking what the hell is going on. Okay, let us say this is Carly A. I can also write it the other way. I can write P plus P minus P0 as a linear sum of Px, Py, Pz. Then again I will get some matrix. So I can write it like this: P plus 1, P minus 1, P0 equal to Carly B multiplied by Px, Py, Pz. And without going through the formal derivation, will you believe me if I say that B is A inverse? Yes. This is quite easily done, right? B equal to A inverse, not very difficult to see that. Now comes the trick. I don't want to work with Carly A and Carly B. I want to work with normal A and normal B, and this is how I define them. Let A be A transpose and B be, okay, let me say it again. Let A be Carly A transpose and B be Carly B transpose. Too many B's. Let us say A is the transpose of Carly A and B is the transpose of Carly B. Now that sounds better. Alright. Why am I taking the transpose? Because if I take the transpose, later on life becomes a little simpler. There is no other reason. And this is the step that Bishop has jumped, and he has only written, please note the subscripts, and gone ahead. Please note what? What am I supposed to note? That is not very clear. This is what you are supposed to note. Yeah, but that's later. So yeah, that's what you are saying. B equal to A inverse. Okay, I hope nobody has a problem with that. Transpose of inverse is inverse of transpose. You can work it out quite easily. B equal to A inverse. Now if I want to write it in terms of the matrix element, what will I write? Basically I call this F, I call this F, I call this G, okay, and will you allow me to write it like this? Fk is equal to sum over L equal to 1 to n. What is A here? A is just the extension of the matrix that we are using. Here for the example we have taken p orbitals where n equal to 3. Now if you extend the same kind of discussion to n dimensional space, right, n dimensional basis, then I can write it like this: F is one kind of functions, G's are the other kind of function, but F has to be written as a linear sum of the G's, and since I am using the transpose here, Fk, the kth F function, is equal to sum over L equal to 1 to n ALK GL. When I say sum over L equal to 1 to n ALK, am I going down or am I going across? I am going down, right? This was my confusion. It is okay because actually I am going across Carly A. Instead of writing that, I have taken the transpose of Carly A, and then of course the rows become the columns. That is why it is written in this manner. Is that okay? In any case, now we are becoming experts in multiplying columns by columns, because even the definition of OR is like that, isn't it? So please don't get confused here. The reason why I write sum over L ALK GL is that I am working not with the actual transformation matrices but their transposes. Why am I working with transposes? Because believe me, and you will see that life becomes simpler a little later if you work with A and B instead of Carly A and Carly B. But until now, is this okay? Fk equal to sum over L equal to 1 to n ALK GL, is that correct? Then I can write the G's in the same manner. I am sorry? If it is diagonal matrix, then what will I get? What will the results be? So then it becomes F1 equal to something into G1, F2 equal to something into G2, so on and so forth. Similarly, I can write Gj. My notation here is a little different from what is used in Bishop, because I want to have one consistent notation. So I have changed this i's and j's and k's a little bit, not much. So Gj similarly will be equal to sum over I equal to 1 to n Bij Fi. What is Gj? The jth element, the jth G function, let us put it that way. What is Fi? It is the ith f function. What is Bij? Bij is the coefficient of the ith f function in the jth G function. Usually it is the other way around. Here it is the other way around, because we are working not with the actual matrices, but their transposes. So now we have got these expressions. What are we trying to do? We are trying to learn how we can switch bases, right?